This lecture will go through IP Multicast basics and the addressing of IP Multicast both at layer 3 as well as layer 2. Very first question here is going to be, what is multicast? Very simply, it is a technique that transfers packets from a single source to many different recipients or receivers. At first glance, it may sound a lot like broadcast, but there is a very big difference. Multicast receivers actually have control on which packets will actually be delivered to them. They can actually express interest, and they can show this interest to the multicast delivery network, and the network will only deliver the packets that the receivers have expressed interest in. In broadcast, there is a much wider scope. So broadcast will take packets from a single source and deliver it to all of the receivers. In multicast, not so much, only the interested receivers. Now, another form of this one-to-many packet delivery could also be replicated unicast. But what distinguishes true multicast, and for that matter broadcast, from any form of replicated unicast is how a source actually behaves. So the source of that multicast, those packets, how does it behave? In multicast, true multicast, the source will ever only transmit a single copy of any unique packet. The packet is replicated later somehow and delivered to the recipients, and that's what this whole course is all about. But the thing to know here is that a multicast source will only create a single copy of that packet. Now, this is true multicast. Replicated unicast, the source would have to create at least as many copies as the known number of receivers. So if it has 100 receivers that it knows of, it'll have to send 100 unicast packets, one for each one of those receivers. So there are some advantages for true multicast versus replicated unicast. One of those may already become obvious, and that is the utilization or the resource utilization at the source. It has to create one copy of a unique packet in multicast versus a multitude of copies, one for each receiver, as we said before, in replicated unicast. There's also better bandwidth utilization. So, like I said, packets will be replicated somewhere. It happens to be actually inside the multicast core, which we'll also talk about later, but they're also done on an as-needed basis. No single link in a multicast network theoretically should have multiple copies of the same packet. That is not true for replicated unicast at all. One link, at least the link between the source and the very first hop router, may have as many copies as there are receivers. So there is better bandwidth utilization definitely with multicast, true multicast. There are also advantages compared to broadcast. In broadcast, or in true multicast versus broadcast, there is better resource utilization at the receiver. The receiver in multicast does not receive any unwanted packets. As we said before, the receivers actually have a technique to signal interest in certain packets, and they will only receive those packets. Whereas in broadcast, they have no control over this. They will be sent all of the packets that have been broadcasted, and then they may have to drop the packets that they're not interested in. That's not good resource utilization. It's much better in multicast. There's also better bandwidth utilization. The packets are now replicated by the network devices only if requested by the receiver, which is not true for broadcast because the packets are just ad hoc replicated. That brings us to IP multicast. The first thing to realize if you're coming from a unicast world, which most of us are, is that just like IP unicast, IP multicast is a packet delivery system. Ultimately, all of the stream, the multicast stream, is delivered inside of IP packets. Furthermore, the header of those IP packets, or the structure of those IP packets, is absolutely identical between IP unicast and IP multicast. You just address it a little bit differently. And where that addressing change takes place becomes extremely important. The very first thing to realize is what remains same. So, if it is same, then you really don't need to pay too much attention to it. This would be the source IPs in those IP packets. The source IPs in IP multicast packets remains exactly the same as unicast. That means they are just the IP address of the source. Take, for example, a single source that creates a multicast packet and creates a unicast packet. If you were to look at the source IP field of both of these packets, it would be absolutely the same, simply identifying the source. The difference between a unicast and a multicast packet is actually in the destination IP field. The destination IP field in multicast packets now represents what is called a multicast group. This would be the collection of the individual receivers that are interested in those packets. Now, when a multicast packet actually gets to a multicast router, the router should have an easy way to distinguish between the unicast and the multicast packet. So one of the easiest ways to do that was to actually create a whole new class for multicast IPs. So all multicast IPs belong to a special class within the IP space called Class D. What is the qualification for Class D? Any of the IP addresses in binary that start with the bits 1110, they all belong to Class D and they all represent multicast groups. If you were to actually do the math on this, the binary math, you would find out that this range actually starts from 224,000 and it goes all the way up until 239, 255, 255, 255. That's about 2 to the power 28 addresses, or roughly 228 million addresses. That's how many individual groups you can actually have with IP multicast. The other major distinction for Class D is it is considered a flat IP space. So there is no concept of subnetting or networks when it comes to Class D. So for Class A, B, and C, you always had networks, you had subnetworks, and you had to worry about all of the various things. With IP multicast, that actually becomes much easier. Every single IP inside Class D simply represents a multicast group. So if I was to look at the very first multicast group that is available, or group number 0 or group number 1, whichever way you want to think about it, it would be 224.0.0.0. As opposed to that, if I was to look at the very last group, the 228 million whatever change group, that would be 239, 255, 255, 255. Number 2 would be 224.0.0.0. And one before the last would be 239, 255, 255, 254. So there are some reserved addresses, etc., but ultimately every single IP represents a multicast group. So it is more simplistic in that particular way. Now, just like unicast IPs, classes A, B, and C, there are some reserved subranges within Class D. Now, these are not subnets. They're essentially just ranges of IP addresses within this class. So even though I'm using CIDR notification, it is essentially just a shorthand to represent that range. It by no means means that this is a subnet. That concept is gone. That concept doesn't exist in Class D. For example, when I say 224.0.0.0/24, all I mean to say is all addresses that start at 224.0.0.0 and end at 224.0.0.255, or those 255 addresses, or 256 addresses. So the CIDR notification, just subranges, not subnets. Let's look at these classes, or the most important ones for this lecture series. The very first one is going to be what is called the local network control block. These are the ranges, or this is the range of IP addresses that are used by well-known routing protocols. The major distinction here is they are limited to operating within a link local scope. They're not supposed to go off a VLAN. This is also accomplished on the back end with a TTL of 1 or 2. TTL of 2 is for those weird NBMA infrastructures where the distance vector routing protocols still they need another router to send packets within that VLAN, but not much use with frame relay now, kind of gone away. But ultimately, if you think of TTL of 1 and the packet never leaving the local VLAN, you're thinking of local network control block. Now, some of the major examples here are 224.0.0.5 and 6 for OSPF, and 224.0.0.9 for EIGRP. Hopefully, these are well known enough. The next range of interest here is 232.0.0.0/8. This is as big as an entire class A block, and these are reserved for source-specific multicast addresses, or it's called the source-specific multicast block. This addressing is used for multicast streams whose sources are already known by the receivers. Now, later on, we'll realize that for the vast majority of IP multicast, this is not true. You never really know about the sources, or you need multiple sources that are delivering to a group, and you need packets from all of them. But there are some occasions where you actually know the source address, and for those, source-specific multicast block has been designated for use by default. You can use other blocks, but if you just go by the default, it's going to be within 232/8. The final one of interest, and the one we are going to be using heavily in our lecture series, is 239.0.0.0/8. This is called the organization local scope, but you can also think of those as private IPs, kind of comparable to RFC 1918 IP addresses. Their use should be limited to within an AS or between ASs that you have some sort of understanding. Ultimately, they should not be leaked to the internet or the I2 or wherever there is global multicast. So 239, it's been set aside for private IP use, and any organization can use any addresses out of it without having to expect any conflict with any other organization. But again, the traffic is not leaked to the internet, so there is no conflict there. So where there is an IP packet, it must be contained inside some sort of layer 2. The predominant technology here is going to be Ethernet. So we will be talking about the MAC addressing, but ultimately if you have a layer 3 packet, it must be contained inside a layer 2 packet. When you start talking about the layer 2 packet, you would realize that at least for Ethernet, you need a source MAC address and you need a destination MAC address. Think back to ARP. Why was ARP needed? ARP was really needed for the creation of a legal layer 2 frame with a well-known MAC address that is understood by the receiver. The contents, like we discussed, of an IP multicast packet will define what addressing is used as at layer 2 for the layer 2 frame itself. Think back to the previous slide. The source IP of an IP multicast packet was unicast. Therefore, there is a one-to-one correlation between the IP and the MAC. So the source had an IP, the source also had a MAC, and you could very easily use the source MAC address for the source IP address, source MAC address for the actual addressing of the layer 2 frame. This also changes when you go off of a VLAN, but ultimately what you will find here is either the either the MAC address of the source or the MAC address of the gateway. Essentially, you have the same logic that you would use for unicast packets. So if you understand how the source MAC address of a unicast packet gets used, it is the same source MAC address in a multicast packet. This is literally one-to-one as the source IP was, unicast and unicast. The destination IP is multicast. Now we need a suitable MAC address to represent that destination IP in the layer 2 frame. What is the final goal here? The final goal is that the receiver and the sender have to agree on a single suitable destination MAC for a single group. So if I have an interested receiver, it should accept frames with the destination MAC that has been programmed by the source at layer 2 for a certain group. That means if I join a group, I should always expect the layer 2 frame that contains a packet for that group to have consistent MAC addressing. So ultimately, what are we trying to do? We are trying to take the layer 3 packet and we are trying to encapsulate it inside a layer 2 packet. So the receiver already knows which layer 3 multicast address it is interested in. And where does this come from? So that information has to come from somewhere, right? Usually it comes from the application layer, whether you have a video streaming application, whether you have some sort of a VoIP or a conference call or something. But ultimately, the application layer knows which layer 3 multicast address from class D it's interested in. This information then starts working its way down the stack and reaches layer 3, where ultimately the NIC, the network interface card, of that receiver is now tuned to this layer 3 multicast address. So think of somebody tuning the radio and finding the right station. In this case, you're finding the right layer 3 multicast address, and now you're listening to packets that are received with that destination multicast address. But before the NIC actually receives the layer 3 packet, it also needs to accept the layer 2 frame carrying the multicast packet. So the layer 2 frame must be accepted before the layer 3 packet can be extracted. For unicast, this was sort of easier. This was the NIC's burnt-in address, and sometimes you change it by configuration, but the NIC is aware of that MAC address. That MAC address belongs to the NIC. And you always provided that to the sender, whether it was a source on the same local VLAN or whether it was your gateway. The receiver would provide this address to them via ARP. It is not that simple for multicast. For multicast, this address, number one, must be dynamic, and it has to be well known. There are reasons for both of these. The address should be dynamic because layer 3 multicast groups are highly arbitrary. You may decide to join a group, leave a group, join another group, leave another group, and so on and so forth as the user changes the streams that they are interested in. Because of that, there is no consistency in layer 3 multicast group that you're listening to. You may be listening to one layer 3 multicast group at time X, and at time Y, you're listening to something completely different. So that's why the layer 2 addressing must be very dynamic. Now, layer 2 addressing also needs to be well known because for the NIC to receive a unique layer 3 multicast packet or a multicast group, they need to always have a consistent layer 2 address. So it has to be well known in the sense that if I know my layer 3 group or the layer 3 IP, then I must be able to correlate it to a layer 2 MAC. How do you provide this? So to provide both the dynamic as well as the well-known qualities, a simple mapping procedure is used. So you will take the IP multicast address, the basic group that you're listening to, and you will use that to generate a well-known MAC address. So how does that mapping of a layer 3 IP to a layer 2 MAC actually happen? The very first thing is to choose a MAC OUI. So that's the first 24 bits of any MAC address that tells you something about the vendor. There is no particular vendor in this case, but 01005E, those 24 bits, that combination, essentially identifies IP multicast. Now the big confusion sometimes that I've seen is all multicast. For example, spanning tree. Spanning tree is not IP multicast, so it actually doesn't use the 01005E. Same thing would go for ISIS or STP Plus for Cisco. But ultimately 01005E, that is only for IP multicast. Now it's worth to take a look at the first 8 bits. So these right here, if I expand them, they go to 0000, 0, 0, 0, and then followed by a 1. This last bit, the 8th bit, holds special significance when it comes to MAC addresses. This is called the individual global bit. Individual group bit. In that, if this bit is fixed to a 0, that signifies an individual address or a unicast address. If it is programmed to a 1, it identifies a group or multicast. So you can see the way this Mac OUI has been chosen, it is consistent with that rule. 01005E always signifies a multicast MAC address. So multicast IP address, multicast MAC address, and everything is consistent. Looking further at the structure of the MAC address, there are 48 bits in a MAC address. Out of those 48 bits, 24 have been fixed for the OUI. They can always only be 01005E. Furthermore, the last out of the remaining 24 bits, so the bit that comes right after 01005E, or of the remaining 24 bits, the most significant bit, that has also been fixed. It has been fixed to a 0. So that means there is one more bit now that is also fixed. If you subtracted that out of 48, you'd realize there is only 23 bits that can be utilized to map an address. 23 total bits out of 48. And the way we do it is pretty simple. You take the lower order 23 bits of the IP, and you simply copy those bits onto these remaining 23 bits. That leads to a little bit of ambiguity. So 28 bits being copied onto 23 bits. And why 28 bits? So think of an IP address. IP address is a total of 32 bits. But out of those 32 bits, for multicast IPs, as we discussed before, 1110 or the first 4 have already been fixed. That means you have a dynamic number of bits that is left to 28. Out of those 28, you can map 23 of them, so the lower order 23 out of the 28 can be mapped, and that leaves 5 bits that have not been mapped. So the 5 bits in IP have not been mapped anywhere. Those 5 bits kind of are lost in an ether. Because these 5 bits are lost, think about how many potential addresses can they represent. Each of those 5 bits could either be a 0 or be a 1. So doing binary math, that's 2 to the power 5. That's a potential 32 addresses that can all map to the same MAC address. So what happens essentially is 32 IP addresses are all mapping to a single MAC. So for example here, if you look at 230.123, 233.129.23, and 239.123, and if you did all of the operations here, so you took a MAC address 01005E, you fixed the next bit to 0, and you took the lower order 23 bits from here, and from here, and from here, they would all map to the same MAC address, 01005E, and then 010203. This is a potential problem, but if you look inside any /8 group, so if you look at 230/8 or 239/8, the possibility of that collision is reduced to, within that /28, which is a lot of addresses, the possibility of a collision is reduced to a 2. So it was deemed acceptable. Now there is a very interesting story that goes with it. This essentially, this whole collision and this ambiguity, it represents a savings of about $15,500 in 1989 dollars. So as the story goes, Steve Deering, who essentially came up with this mapping in one of the RFCs, I think 1112, he calculated how many total OUIs it would take to map the entire multicast IP space. And that came out to, and if you did your calculations, you would find out that that came out to 16 OUIs. If he had 16 OUIs, consecutive or non-consecutive, then he would have been able to map all 28 bits. Now, each of these OUIs cost $1,000 or so back in 1989. So he could only, or the organization that he was working for, could only afford one OUI out of these. Now, that one OUI was basically, to add insult to the injury, that one OUI was actually split into two. And that's why this bit here is fixed to 0. Because that OUI, the 01005E, was further split into two for two different projects, and only the top half was given to Steve Deering. So he did the best with it that he could, and that is why we have this ambiguity today. But if you look forward to IPv6 multicast, which we will cover in a different lecture, that ambiguity actually explodes. So really, it's a moot point. Ultimately, you have 128 bits, and out of that, some of them are fixed, and you're trying to map it to 48. No matter what you do, there's going to be some collision. So ultimately, it's not that big of a deal. Most of this happens automatically anyway. But if you were to look at a packet capture, this is what you will see. We will see you again with another lecture trying to complete this series. Thank you.